So we're going to talk about derivatives and integrals of vector functions. And guys, if you know your derivative and integral rules, this will be kind of a piece of cake, right? The derivative of a vector function, if r of t is equal to f of t, g of t, h of t, where f of f, g, and h are differentiable, then the derivative r prime of t is just equal to the vector where the components are the derivatives of the functions f, g, and h. And for definite integrals, it's if you take the definite integral of r prime of t dt, then it's going to be equal to a vector where the components are just the definite integrals with the bounds a and b of f, g, and h. So that's really kind of all you need to know, as well as the fact that all of the differentiation rules work the same, right? So if this is from the book, but you could see, all of the rules like chain rule, product rule. Interestingly enough, quotient rule is not on here, but I guess you can't really divide vectors. I don't know why. I don't know why that didn't just. I don't know why I just said, wow, quotient rule's not on there. I just realized why you can't really divide vectors, at least not that I've seen so far in the book. But because a little secret, I'm really learning this all with you guys. But point is that really all the rules work. And one thing I want to just kind of talk about is that really what r prime of t is it's really just the limit as h approaches 0 for sorry, I just lost my train of thought. R t plus h minus r prime of t over h, right? That's the deal. Now, if you were to think about like a curve, like a space curve, right? Remember, a space curve is really just a vector function, like the point, the path traced out by the tip of a vector function, right? If you think about r of t. Well, right? So, if you were to think about, okay, well, there's going to be some point in time, t plus h, where the vector will kind of look like this. And this right here is going to be that if I were to do my tip to tail, or if I were to do vector subtraction, this right here, that from there to here, I can do it with a different color just so it's a little bit more clear. But this is this right here is r prime of t plus h, right? If this is r prime of t plus h, or r of t plus h, well, this is r t plus h minus r of t. So that's the subtraction of it, like if I were to subtract the two vectors, and then if I were to take that quantity and divide it by h, then it's just going to be a scalar multiple. So it's going to be something like that. And then as you can imagine, as h approaches 0, so I can maybe blow this up so I can make it look like that. As h approaches 0, if this was this is our space curve, then you can imagine that, well, over time, the difference, it's weird because it's like over time, the difference would approach 0, right? Because if you think about as h approaches 0, but then you're also multiplying the vector, right? So r prime, or r of t plus h minus r of t, right? It's just gonna, if this is h, as h approaches 0, you're just getting the same vector, but also you're multiplying it by 1 over h. And h is getting really small, so this scalar multiple, right, it's going to end up getting pretty large. Not infinitely large, because it's this weird thing of like, the vector itself is approaching like 0, but then you're also multiplying it by 1 over h, which is approaching infinity. So you eventually get, as when you take this limit, you eventually get something that looks like this. oh my god, I keep dropping stuff. But you eventually get this. And this is the derivative, r prime of t. And you notice it is tangent to the space curve. That's what I was kind of trying to show you with the whole, as it's approaching 0, it's going to become tangent. And when you multiply, it's like that thing of like, oh, the difference is approaching 0. You multiply it by 1 over h. 1 over h approaches infinity. You get that indeterminate form. But when you actually when you do the limit definition of the derivative, when you take the limit and you get the derivative, it just ends up being tangent to the space curve. So if I wanted to find the unit tangent vector, meaning what is the vector at this point, that's a unit vector but tangent to the actual space curve, well, it's pretty simple, right? I'm just going to do r prime of t divided by the magnitude of r prime of t. And this is, and you know, that's how you get the unit vector of anything. And let me just check my notes to see what the notation was. Like yeah, I think they use a big T. So big T, unit tangent vector of t. So this is the unit tangent vector. So this is just to give you an understanding of derivatives. As for integrals, I still need to take more time to fully conceptualize what it means to take the integral of a vector function, right? Because we know integrals, like a definite integrals, looks at the area under a certain curve. I don't know how that applies to surfaces, or I guess in this case curves, really, because a vector function is a curve, but it's like a curve in space. I need to take some more time to think about that. But the integration rules will also apply, because if all the differentiation rules work, then the backward integration stuff will work too, if that makes sense. Because at the end of the day, you're taking the integrals of scalar functions, so you know all your scalar integration rules will still apply. I guess there aren't really any properties of, I don't know. I'm trying to think of, like, you know, we have the derivative rules, and it's like we don't really have integration rules. We more so have integration strategies. So obviously those still work because they don't really. They're more like U sub is not a. That's just a general strategy. Hopefully you get what I'm saying. I'm gonna quickly do an example problem, and then this is really the entire lesson is just knowing this stuff. So I'm just gonna do an example. Let's say we have these two curves. Let's say we have these two curves. Okay, so let's say we have R1 of t, which is going to equal like t, and then t minus 1 minus t, and then t squared plus 3. And then we have R2, and we'll use a different variable s, which is going to equal 3 minus s minus 2 s squared. At what point, so we're going to ask, what point do the curves intersect? Okay, so at what point do the curves intersect, and then what is the angle made by the curves at the point of intersection? That's a question we're going to try to answer about these two vector functions. So here's how I'm going to go about doing it. Well, I want to first check, well, hey, when are the x's going to be equal? Okay, so when is x1 going to equal x2? And I'm just right now trying to find at what point do they intersect. So I know x1 is going to equal x2 when t is going to equal 3 minus s. So when t is equal to 3 minus s, I know that they are going to be equal, or in other words, when s is equal to 3 minus t, which we don't really need, but it's fine. Yeah. So then, when are the y's going to be equal? So when is y1 going to equal y2? Well, they're going to be equal when 1 minus t is going to equal s minus 2. But this equation right here tells us when the x's are equal. So ideally, for intersection, we want the x's to be equal, we want the y's to be equal, we want the z's to be equal. So I'm going to use this little equation, I'm going to use this fact that, hey, when t is equal to 3 minus s, that's when they're equal. I'm going to use that over here and say, hey, well, 1 minus 3 minus s is going to equal s minus 2. And then I get, so I get essentially s minus 2 needs to equal s minus 2, which this isn't very helpful. So this is really telling us that the x's are always equal to the y's? Is that what that's telling us? Or it's telling us whenever the x's are equal, the y's are always equal. I'm not too sure. I need to think about it. But in this case, we can go to the z's, and we could say z1 is going to equal z2. So we could say, hey, so t squared plus 3 is going to equal s squared. So really, I get, 3 minus s squared plus 3 equals s squared. So then I get 9 minus 6s plus s squared plus 3 is equal to s squared. Luckily, one of the s squareds cancel out. And then I get 9 plus 3 is 12 is going to equal 6s. S is going to equal 2. And then going back over here, I can say, hey, well, when s is equal to 2, t is going to equal 1 when the x's and the z's are equal. And it seems like, I think what this is saying, I could be wrong, but this is saying, hey, when the x's are equal, the y's are always equal. But that doesn't really make sense. I don't know. I have to think about it. But I essentially get these two values. So I could say, hey, r of 1, right? R of 1 is going to equal 1. 1 minus 1 is equal to 0. And then 1 squared plus 2 is 3. 1 squared plus 3 is equal to 4. I was like, that doesn't look like the key. But you can do the same thing for r of 2, and you should get the same thing, right? And you see you do. 3 minus s is equal to 1. 2 minus 2 is equal to 0. And 2 squared is equal to 4. So they intersect at 104. 1 minute. So now we can see this is where they intersect. So I can now try to figure out what is the angle between the curves where they intersect. And really, this is just asking what is the angle between the tangent vectors. So how do you find the tangent vector? Well, we know a tangent vector, there's really an infinite amount, but a tangent vector is really just the derivative of the vector function. And I say there's an infinite amount of tangent vectors because after that, it's just any scalar multiple. So we're kind of running out of space here, but I'll just do it here. So I know r prime of t, not a terrible integral, or not a terrible thing to calculate, but so the derivative of t is 1, the derivative of 1 minus t is negative 1, and the derivative of t squared plus 3 is going to be 2t. And then r2 prime of s, well, the derivative, of 3 minus s is negative 1. For s minus 2, it's 1. And then for s squared, it's 2s. So at r prime of and what I can actually do just to make my life a little bit easier is I know that, hey, when I'm going to be computing this integral, I guess it doesn't actually matter. It's fine. Never mind. Just don't worry about that. So r prime of 1 at t equals 1 is going to equal 1, negative 1, 2. And then at r2 prime of 2, because that was the values we calculated where the curves intersect, is going to equal 1, negative 1, and 4, I think, right? Yeah. So now, or I should say negative 1 and 1 here. So now we can calculate the dot product. So we know the dot product, so r1 of 1 dot r prime of 2, or r2 prime of 2 is going to equal, so 1 times negative 1 is negative 1, plus 1 times negative 1 times 1 is plus, or minus 1 again. 2 times 4 is equal to 8. So we get plus 8 and equals 6. Okay, and now the dot product by the dot product theorem thing is going to equal the magnitude of r prime of is going to equal the magnitude of r1 prime. So square is going to equal square root 1 squared plus negative 1 squared plus 2 squared. So 4 plus 1 plus 1 is going to equal 6 times root 1 squared plus 1 squared plus 4 squared is 18 cosine theta, right? So I'm taking the magnitudes multiplied by cosine theta. This, you can do a neat little trick here. You can be like, well, hey, I just want to get rid of this. I can get a 6 on both sides by multiplying both sides by root 6 times root 6. This root 6 and this root 6 on the right-hand side just turns into regular 6 because you're taking the 2 square roots and multiplying them. And then the 6 will then drop on both sides, which is, it's like, it's the same thing as doing that thing where you rationalize it or whatever. This is kind of what we're doing. I think it's like reverse rationalizing. But, I guess we are rationalizing. But then you eventually get that cosine theta is going to equal root 6 over root 18. And then my theta will just be cosine inverse of root 1/3 when you simplify this. So yeah, this has been derivatives and integrals of vector functions. Hopefully this made a little bit of sense. Thank you for watching.